In the first week, we talked about propositional logic and logical functions, operators. And this week, we are going to talk about first order logic, quantifiers, negation, and nested quantifiers, and pre-next normal form in the context of first order logic. And finally, we will talk about arguments and inference, both in propositional logic and first order logic. And we will especially uh, give weight to the resolution principle, which is quite useful when dealing with arguments. So we will start with first order logic, which is also called predicate logic. If you remember, when defining the concept of proposition, we have seen rules to talk about the truth values of propositions, such as, let's say, 2 plus 2 equals 3, etc. But we said that a statement in the form of x is greater than 2 is not really a proposition because we do not know the value of x. So we cannot assign a truth value to this statement. So to handle such cases, we define predicates or propositional functions that applies the statement or the predicate is greater than 2 on the variable x. So for instance, if you define the propositional function p of x to denote x is greater than 2, then x is greater than 2 can be made into a proposition. For instance, if you apply the value 5 to this propositional function, then p of 5 is true. Similarly, you can say that p of 0 is false. Propositional functions can also take multiple inputs. For instance, you can define this function q of xy to mean x plus y equals 0. So the context which we will talk about the predicate functions is the first order logic. And this also means sometimes we can refer to the propositional logic as zeroth order logic, which also implies the existence of higher order logics, second order, etc. But we are not going to discuss those. Okay, let's define the concept of a quantifier. Quantifiers are used to denote the truth values of propositional functions in generalized cases. How so? Let's see this in specific cases where we discuss specific quantifiers. And these three are the most prolific ones that you would see. And especially the first two are indispensable. The first one is universal quantifier, for which we use this symbol, and we read it as for all. And this indicates that the predicate is true for every possible value the variable can take, without exceptions. The next one, the second one, is called existential quantifier, which we use this inverted E symbol to denote, and we read this as there exists, or sometimes there is. This indicates that a predicate is true for at least one value the variable can take. So this is talking about existence of the truth of a statement. And we also have what we call the uniqueness quantifier, and it is denoted using this symbol. And we read this as there exists a unique such and such, or sometimes you see there exists one and only one, whatever that is. Okay, so these are the most common quantifiers. There are others which we will not discuss, but even the uniqueness quantifier is not very widely used, and we will see the reason for this later on. Okay, in a general sense, here you see how we treat the truth values that can be assigned to statements involving quantifiers. Here you see for all x, px, and px here is a propositional function. And for this statement to be true, this propositional function must be true for every possible x in the domain. every one of them without a single exception, okay? Even if you have one single exception for which p of x is false, then this statement in its entirety will be false. On the other hand, when we have existential quantifier, this is true when there is an x for which p of x is true. There is an x. So this talks about existence, okay? It doesn't care about the number. It could be 1, it could be all of them, it could be 2, it could be 7, but it's not 0, okay? There is at least one for which p of x is true. At least one x value that makes p of x true, okay? And it's, of course, it's going to be false when for every x, p of x is not satisfied. And finally, let's talk about the uniqueness quantifier. And the uniqueness quantifier here, there exists a single x such that p of x. This statement is going to be true when there is a single x for which p of x is true. Okay, as the name implies, this quantifier is related to existence and uniqueness together. So there must exist something that satisfies p of x, but that thing should be unique. Okay, if you have 2 or more, then uniqueness quantified statement will be false. Okay, so there are 2 cases where the uniqueness, the quantified statement can be false. Either p of x is false for every x in the domain, okay? So there is no single x value that makes p of x true, or it's also false when there are more than one that makes p of x true. Okay. Here are very simple examples. For all x real, okay, so this indicates the domain, x squared is greater than 0 is true. I'm sorry, this is for existence. So there exists an x, which is a real number, such that x squared is greater than 0. This is true since it holds for 1. Just one exists, one sample is sufficient here to conclude the truth of this statement, because this quantifier deals with existence. It doesn't care about how many, it just quantifies existence. On the other hand, if you look at this, this says for all real numbers x, for all, okay, x squared is greater than 0. This is false. Why? Because, well, this statement is true for all real values except 0. So it has one single exception at 0, which makes the statement false. Now here you see the domain of this quantified statement, the domain in which your x variable can take values in. This is crucial, and next we will talk about this.